Our next section in Chapter 11 is 11.3, Inference about two means with independent samples. So this is going to look pretty familiar and similar to what we just went through in 11.2, which is nice because with just this subtle change in formulas, the process remains relatively the same. So we're getting a lot of practice in those same. So we're going to do test hypotheses regarding the difference of two independent means. In the last 11.2, we did dependent samples. And then we're going to construct and interpret confidence intervals regarding the difference of two independent. Sampling distribution of two means, independent samples with population standard deviations unknown. Suppose that a simple random sample of size n1 is taken from a population with an unknown mean, mu sub 1, and an unknown standard deviation, sigma sub 1. In addition, a simple random sample of size n2 is taken from a population with an unknown mean, mu 2, and an unknown standard deviation, sigma 2. If the two populations are normally distributed, or the sample sizes are sufficiently large, greater than 30, then the sample statistic t is found as follows. T equals x bar 1 minus x bar 2 minus the quantity of mu 1 minus mu 2 all over the quantity of the square root of s1 over n1 plus s2 squared over n2. Okay, and this approximately follows the t distribution using the degrees of freedom from the smaller sample size. So this is one of the first key things, really key things here, is that when we're using our table and looking at degrees of freedom, we now have two samples here, and what we're going to do is we're going to use the smaller sample size if they're not the same. And then x bar and s are simply the sample means and standard deviations for each of the sample populations. So obviously x1 is the mean for the population 1, and x2 would be the sample mean for the sample, second sample. Okay. To test hypotheses regarding population means with unknown populations, we can use the following steps provided the sample is obtained using simple random sampling or through a completely randomized experiment with two levels of treatment. The sample data is independent. The populations from which the samples are drawn are normally distributed, or the sample sizes are large, again, n greater than or equal to 30. And of course, for each sample, the sample size is no more than 5% of the population size. So this is nothing new to us. And it's really just the caveat to look at the two different the methodologies for. First, let's look at the classical approach, and this should look very familiar. Step one is, of course, to determine the null and alternative hypotheses. Here, the null hypothesis is that the average from the first sample is equal to the average from the second sample. And of course, the three different approaches are that those means are not equal, two-tailed. One mean is less than the other left-tailed, or greater than for the right-tailed. The second step in is to select a level of significance. And the third is to compute the test statistic. And we just saw this new formula, which is the first thing here. And also, we'll note that we're going to be, when we're talking about degrees of freedom, we're going to look at whichever sample had the smaller sample size when calculating the degrees of freedom. In the formula, of course, the values of x bar and s are the mean and the standard deviation of the specific sample pool. Okay. From there, what we're going to do is we're going to use table 7 to determine the critical value. Remember that for two-tailed, what we're looking at is plus or minus T alpha over 2. And for left-tailed, we're looking for negative T sub alpha. And of course, for the right-tail, we're just looking at T sub alpha. And remember that table 7 is a right-tailed table, so it really is talking about the area to the right, but because it's a symmetrical distribution, for the left-tailed, we can just take the opposite value of this, negative t sub alpha, excuse me. Okay. From there, we then compare our test statistic with the critical value that we found in the table, and we reject the null if the test statistic is in any of these critical regions, depending upon which approach we're using. Again, none of this is new. The only thing new here so far is our test statistic that we're looking at. And then, of course, we state the conclusion. If we're looking at the p-value approach, the first 3 steps, at least through the middle of step 3, are the same as for the classical approach. The calculation of the test statistic is the same, but the difference is now we're going to use table 7 to approximate the p-value. And this is when we use the values across the top, that we tend to think of those also as alpha values. But now we're trying to use the test statistic and the degrees of freedom to figure out what column heading we use, and that represents the p-value, which represents the area in the shaded region. Okay. And so again, what we're going to do here is, because table 7 is really a right-tailed table, for the left-tailed table, we won't use negative. We'll just use that same t sub 0 value and look at the table to figure out the area because it's symmetrical. And then if we have a two-tailed approach, then we're going to double that area. We're going to find the t sub alpha and then just double it again because it's symmetrical. Here we compare the p level and the level of significance, the p level that we found. And remember, we reject the null if the p-value is less than alpha. Okay. And remember, this should make some logical sense to you. A p-value you might think of as a probability that we're going to have values in that area. And here, the alpha value is something we select that says, we want to have 95% confidence, which means that alpha is equal to 5%. And so if this p-value is less, that would mean that we don't have that 95% confidence level. So that kind of makes some good logical sense as well. And then, again, we state the conclusion. So let's go walk through an example so you can see this, but it should feel pretty similar to what we've done. The only difference here is that we have a new calculation for our test statistic. So make sure you get that in your notes and you memorize that. And similarly to what we just saw with dependent data, the independent procedures are also robust, which means that minor departures from normality will not affect the results. But again, we cannot use this method if there are outliers. So looking at the example, in the Space Lab Life Sciences 2 payload, 14 male rats were sent to space. Upon their return, the red blood cell mass in milliliters of the rats was determined. A control group of 14 male rats was held under the same conditions except for spaceflight as the space rats, and their red blood cell mass was also determined when the space rats returned. The project resulted in the data listed in Table 3 on the next slide, actually down below. Does the evidence suggest that the flight animals have a different red blood cell mass from the control animals at the alpha equals 0.05 level of confidence? So we can see that just from this statement at the end that we're talking about a two-tailed approach, because we're just asking if they have a different, not if it's greater than, not if the flight rats are greater than the control group or vice versa, or less than, etc. Okay. This figure shows the normal probability plots of the data. We have the box plots here of the control and flight, and then here we have the normal probability plan of the flight rats and then the control rats. The correlation, which we talked about before in 11.2, between the red blood cell mass in the flight group and the expected z-scores is 0.984. The correlation in the control group and expected z-scores is 0.973. Both 0.984 is greater than 0.935. Now remember, this is from table 6, based upon the degree of freedom and the number of the number in the sample. And then also 0.973 is greater than 0.935. Since both of these values are greater, the correlation values are greater, it's reasonable to conclude that the data comes from populations that are normally distributed. So we go ahead, if we look at the box plots, it seems that there's not much difference in the red blood cell mass of the two samples. Although the flight group might have a slightly lower red blood cell mass. What we have to do here is to determine if this difference is significant or due to a random sampling error, and that would be the chance or coincidence. So now that we've validated the data, we can go ahead and do our analysis using the classical approach. The first one is to determine the null and alternative hypotheses. In this case, we know that the null regarding two means is always that they're equal, and since our hypothesis is about those values being different between the flight and control groups, this is a two-tailed test. Our level of significance is 0.05, and so the first thing we need to calculate is the test statistic. If we look at the data from the flight group, we have a mean of 7.881 and a standard deviation of 1.017. And for the control group, we have a mean of 8.340 and a standard deviation of 1.005. In both cases, we had the sample size was 14. So plugging in all those values and calculating, we get a test statistic, T0, of negative 1.437. So now we need to pull out table 7 to determine the critical value. Now, since our sample size is 14, our degree of freedom is going to be 13. Remember, with a two-tailed test, the critical values are at T alpha over 2. Well, alpha is 0.05, so 0.05 over 2 is 0.025, and so we go to the column heading for 0.025, and we find that the value there, the critical value that lines up with 0.025 for alpha and 13 degrees of freedom is 2.160, okay? So what we need to do now that we have the critical value and the test statistic is we need to compare them to determine if we support or reject the null hypothesis. So here we have a diagram. Here is the critical regions at negative 2.160 and 2.160. And remember that we reject the null hypothesis if our test statistic is within the critical regions. In this case, it is not. You can see the test statistic there, negative 1.437, is outside of either critical region. So in this case, we would not reject the hypothesis, and we would state the conclusion as follows. The sample data does not provide sufficient evidence to conclude that the flight animals have a different red blood cell mass from the control animals at the alpha equals 0.05 level of significance. We could do the same example using a p-value approach, and if we did that, notice that just like before, the first three steps are largely the same. We still calculate the test statistic, and it's still the same formula. So we've already gotten halfway through here, okay? when we're using the p-value, what we're looking for is the areas, right? And think of these as kind of connected to probability. So here we have to figure out, we use the test statistic and the degrees of freedom, which is 13. 14 minus 1 is 13, right? The sample size minus 1. Since they're both the same, it doesn't matter which one we use, but if one was smaller sample size, we would use that one. So we go across the row trying to find the value of negative 1.437. There aren't any negatives. Remember that what we're looking at is the positive and negative because of the two-tailed approach. So we're just going to use the absolute value of that of 1.437. And as we go across, we can see that it's between these two values, 1.350 and 1.771. Now this corresponds to the p-values that you see at the top. Now you might think of these as alpha values as well, but remember alpha is connected to a kind of a conceptual probability as well, and p-value is a probability concept too, so that could work out as well. So we know that the p-value is between 0.10 and 0.05. But that, be careful now, because remember that's only given us one area, okay? And specifically the area to the right here. And so to calculate the actual p-value for a two-tailed test, we have to find that one area, which we did, which is between here and here, but we have to multiply it by 2 because it covers both feet, if you will, of the distribution. And then because it's symmetrical, we can take one area and multiply it by 2. So if we multiply all the values by 2, we can now see that the p-value is between 0.20 and 0.10. Our next step is to compare the p-value and the level of significance. And remember, if the p-value is less than the alpha value, that's when we reject the null. In this case, we know that the p-value is between 0.20 and 0.10, which is still greater than the alpha value, which is equal to 0.05. So in this case, we would not reject the null, and we have the same exact conclusion as we had before. If we, in fact, use technology, here we're using StatCrunch, you can see that the p-value comes out to 0.1627, which was between the 0.10 and the 0.20 that we saw before. Again, we compare the p-value to the alpha value. Since it is greater, we don't reject the null hypothesis. One thing to look at, though, is notice the degrees of freedom. Our degree, we only had sample sizes of 14, so the degree of freedom should be 13. But here we have a degree of freedom of almost 26, which is really before. And so the degrees of freedom used to determine the critical value in the last example were conservative. Results are more accurate, can be obtained by using the following degrees of freedom formula. So we can actually calculate a more accurate degree of freedom by using this formula here, and that's for the numerator you get s1 squared over n1 plus s2 squared over n2, and that sum squared is in the numerator, and then we have s squared 1 over n1, that fraction squared all over n minus 1, plus s2 squared over n2, that whole quantity squared over n2 minus 1, and that whole sum is in the denominator. Yeah, that's a mouthful. Okay. So you need to be careful. The degrees of freedom in by hand solutions will not equal the degrees of freedom in technology solutions unless you specifically use this formula to compute the degrees of freedom. So our second objective in this section is to construct and interpret confidence intervals regarding the difference of two independent means. So again, we have the same idea that we have two samples with specific sizes of sample and unknown mean mu and unknown standard deviation sigma. And again, we have to test the data. And if the data is normally distributed or the sample sizes are sufficiently large, then the confidence intervals can be found as follows. X bar 1 minus X bar 2 minus T alpha over 2, that's key, times the square root of S1 squared over N1 plus S2 squared over N2. And again, all of that quantity is taking the square root. Again, the lower bound and the upper bound are only difference by the difference between a difference and a sum. So the lower bound is subtraction, the upper bound is addition. So if you memorize one formula, you've got them both. Okay. So let's look at an example, constructing a confidence interval for the difference of two means. A Gallup poll of 513 national adults aged 18 or older who considered themselves to Republican asked, of every tax dollars that goes to the federal government in DC, how many cents of each dollar would you say are wasted? The mean amount wasted was found to be 54 cents with a standard deviation of 2.9 cents. The same question was asked of 513 national adults aged 18 or older who consider themselves to be Democrat. The mean amount wasted was found to be 41 cents with a standard deviation of 2.6. Construct a 95% confidence interval for the mean difference in government waste and interpret the interval. The samples are independent. They're obtained through a simple random sample. The sample sizes for both Republicans and Democrats are large, 513 in both cases, and the sample size is small relative to the size of the population. Therefore, the requirements for constructing a confidence interval for the mu Republican minus mu Democrat using standard students t distribution are satisfied. So here's the formula again for the upper and lower bound. Remember, the upper is with plus, the lower is with minus. The statistics that we can see from before, the number in the sample was 513, and these are calculated values. X bar Republicans is 54, standard deviation Republicans is 2.9, mean or X bar Democrats is 41, and standard deviation is 2.6. This was all given in the wording of the problem. None of this had to be calculated. So using table 7, and we use 100 degrees of freedom. Now, why do we use 100, right? A degree of freedom, if we subtracted 1 from this, would give us 512. Remember, at the bottom, we only go up to 90, but we go by tens after a while. We have 100, but then we have 1,000 right after 100. So we use the largest value without going over, and so that would be the 100 value. Remember, we're doing t sub alpha over 2, so being that alpha was 0.05, alpha over 2 would be 0.025, and so there we get our value for the critical t value, which is 1.984. If we plug these into the formulas that you can see up here, X bar Republican minus etc., I'm not going to read that again, we get the upper and lower bounds, as you can see here from the calculations, just plugging the numbers in and valuing it. So based upon this upper and lower bound, our statement would be we are 95% confident the Republicans believe the mean amount of each dollar collected by the federal government that is wasted is between 12.7 and 13.3 cents higher than the mean amount Democrats believe is wasted. Okay, so that's how you figure out the confidence intervals, how you calculate them, and then also how you report it. Here we could see using Minitab, we get, again, the 95% confidence interval, and you can see we have the same values, 12.7 and 13.3.